Welcome you all to Principles of Organic Synthesis. Presently we study electrophilic aromatic substitution. In this topic so far we had two lectures. The first lecture we studied the principles and Friedel-Crafts reactions. The second lecture we saw the formylation and Mannich reactions. In this lecture we will try to cover nitration, sulfonation and halogenation reactions. As all of you know very well, nitration is a fundamental and important transformation organic synthesis, because this compound serve as precursor to synthesize variety of compounds that are important in medicinal and material sciences. Here an example shown for the nitration. Usually, as you can see here, and the nitration is done using a mixture of nitric and sulfuric acid. If you carry out the reaction, the aromatic benzene ring, and if you carry out the reaction at 30 to 40 degrees Celsius, you will be able to produce nitrobenzene as a product. Now, if you look at compare the nucleophilicity of this aromatic ring is less nucleophilic comparing to this, because due to the electron withdrawing nature of the nitro group, therefore it does not undergo further nitration at this temperature. However, when you heat the reaction to 90 to 100 degrees Celsius, you can also try to introduce another nitro group at meta position. You can get in this way 1,3-dinitrobenzene as the product. To introduce further nitro group, you have to carry out the reaction under vigorous condition using a fuming nitric acid as well as fuming sulfuric acid mixture. The reaction is very slow. You have to carry out the reaction several days, so that you can end up with a 1,3,5-trinitrobenzene as the product. So, if you want to make this trinitrobenzene, you have to carry out the reaction as you can see here, and under vigorous reaction conditions you will be able to get this compound as a product. However, if you compare the reactivity of benzene with toluene, toluene is about 25 times shows greater reactivity comparing to benzene, because due to electron donating nature of the methyl group. Once if you have the electron donating group, the reaction can be facilitated. Therefore, what normally we do when we want to make trinitrobenzene, we start with the toluene as the substrate. So, when you do the nitration with the toluene, you see a mixture of HNO3 and sulfuric acid, and you will be able to end up with trinitrotoluene as a product. So, instead of doing directly with the benzene ring, what you can do, you start with toluene. So, when you react with a mixture of nitric and sulfuric acid, you will be able to get this trinitrotoluene as a product. Once if you form this one, you can try to oxidize the methyl group into carboxylic acid using K2Cr2O7 in acidic medium. When you oxidize, you can convert into corresponding carboxylic acid. When you heat this compound, you can lose carbon dioxide, and you will be able to get trinitrobenzene as a product. So, this is one of the common method we use to, if you want to make trinitrobenzene, and you can carry out under milder conditions. And once you form this trinitrotoluene, you can try to oxidize this methyl group into carboxylic acid. When you heat it, it can undergo decarboxylation to give trinitrobenzene as a product. Now, let us look at the mechanism of this transformation. If you look at here, you have the nitric acid which acts as a base, and this lone pair can pick up this proton. So, then you will be able to get this and plus this mixture. Once you form this one, now it can lose water molecule. So, you can generate in this way nitronium ion, which is the electrophile in the nitration, And when you take a mixture of nitric acid and sulfuric acid, nitric acid acts as a base, it can deprotonate you can from the sulfuric acid, and you can generate nitronium ion, which acts as an electrophile in this reaction. Once you form this one, now it can act as a nucleophile, can undergo addition reaction, as you can see here. Then you will be able to get this intermediate, carbocation intermediate. Once you form this one, now this can lose proton, and then you will be able to get nitrobenzene as the product. This is low, this is fast. So, simple, if you look at here, so this the substituent also very important. Already we have seen the first class, if you remember, the effect of substituent plays very important role when you do the electrophilic substitution. In this case, and when you have if you take nitrobenzene as the substrate, when you do the nitration, always the nitration takes place in the meta position, not and ortho and para position. It does not take place here, and selectively it undergoes reaction meta position. On the other hand, if you take toluene as a substrate, the nitration takes place ortho para position. There is no reaction at the meta position. So, this can be easily understood by drawing the resonance structure of this intermediate. And for example, if you have the nitrobenzene as the starting material, when you do the nitration, if you do the nitration at the meta position, you have this carbocation, which can you can try to write resonance structure of this carbocation. As once you form this one, now you can write the other one. So, if the reaction takes place at the meta position, you will have these three possible resonance structure. On the other hand, when if the reaction takes place at para position, for example, so what will happen if it happens at the para position? You will have this intermediate. Once this can be written, resonance form of this is, you can try to draw like this. This is least stable, because you can see here you have the electron withdrawing group in this carbon where you have the positive charge. This is less stable, and similarly when you write for the ortho nitration, in case if you want to introduce nitro group ortho position, you can also try to these are the possible resonance structure. If you look at here, this is least stable. So, if you compare the reaction with the meta substitution here, you can have three possible resonance structure of this intermediate. If you compare this one with this ortho, para and ortho substitution intermediate, and you will have the less stable intermediate in both this case. Therefore, whenever you have the electron withdrawing group in the aromatic ring, and when you carry out the electrophilic substitution reaction, always the substitution takes place at meta position. On the other hand, when you have the electron donating group, when you carry out the reaction with the electrophile, the substitution takes place ortho and para positions. If you try to draw the resonance structure of this intermediate for this, then you will be able to find the positive charge will come in this position. So, already you have the electron donating group, and the positive charge can be stabilized more, then you will have the more stable intermediate when the reaction takes place and ortho and para position. Now, let us look at one application of the nitro compound. If you look at here, and this just we have seen nitration, when you take the mixture of nitric acid and sulfuric acid, it is actually a base, this is an acid, you can generate the nitronium ion. Once you form this access electrophile, it can undergo reaction with the aromatic ring, you can get the nitrobenzene, just we have seen. And this nitro group can be readily reduced to amino-amine, and in this case nitrobenzene can be reduced, converted into aniline using tin HCl. Once you form this one, you can try to react with the sodium nitrite and HCl. The temperature is very crucial here at 0 to 5 degrees Celsius, and you can make the diazonium salt as a product. You have to the temperature is crucial in this reaction. This we will study in detail when we see the application of this compound. However, here we will see one application here, and so the nitro compound can be converted into diazonium salt. This can be easily understood if you have the sodium nitrite. So, when you react with HCl, you will form HNO2. Once you form the HNO2, now when you, since you carry out the reaction acid medium, you can do the protonation. So, when you react with one, this can undergo addition reaction here, then you will lose water molecule. So, you will be able to get so this can lose proton. So, you will be able to have so this intermediate, once if you have this one, when you react with aniline, it can undergo addition reaction. So, you will be able to this intermediate, this can convert into by proton transfer. So, when you the presence of acid, you lose water molecule, you make salt diazonium. If you carry out the reaction in the present hydrochloric acid, you will get this salt. So, in this way you can generate the diazonium salt. The temperature is crucial, and so when you have the sodium nitrate and HCl, you can form the diazonium salt. If you have the aniline, you can form this salt, which find wide applications in organic synthesis. Here, once you form the diazonium salt, you can see here, instead of aniline, if you take this as a substrate, and you will be able to form this salt. Once you form this salt, now you can try to react with dimethyl aniline, and you will be able to get methyl orange. So, here shown the mechanism of this reaction. So, you will be able to get this intermediate. Once you have this intermediate, and you will be able to get this salt. This we use as indicator. So, depends upon the pH, and if acidic medium, you can also make protonation here. Therefore, this compound is known as methyl orange. We use as indicator during the titration to find out the acidity of the reaction medium. Another example shown here, let us take this compound orthonitroaniline, at which we use as a precursor to make variety of heterocyclic compound. A cyclic compound, if it has heteroatom like nitrogen, we call them as heterocyclic compound. Orthonitroaniline is used to as a starting material. With other reactant, you can make variety of useful heterocyclic compound. Now, let us look at it. What we found in our lab. Now, when you have this aniline derivative, and when you react this compound and with a mixture of copper 2 chloride and FeNO3, you can see here the ratio 20 mole percent and 35 mole percent. When you take this to mixture and 1 to dichloroethane as solvent room temperature, you mix this one, you will be able to introduce nitro group. You can, in this way you can make the orthonitro derivative. When you go for the effect of substituent, and you can see, for example, the benzene ring can have variety of substituent like methyl group. Here you can have a halogen and methyl methoxy group, and you can have ethyl group. This unsubstituted one. You can see here the substituent present in different position. So, a meta position with respect to this CN bond, and you have here dimethyl group at the ortho position. Here also you have, so you have here methyl group and para position, and you can here nitro group. If we remember, we have seen nitrobenzene is you have to heat at around 100 degrees Celsius, introduce another nitro group to make 1,3-dinitrobenzene, but here at room temperature, using this combination of this copper 2 chloride FeNO3, you can try to introduce nitro group. And you can see here, if you have the nitro group para position, you can introduce another nitro group, meta with respect to this nitro group, ortho with respect to this amino group, you can introduce another nitro group. And you can also have amide, for example, astamide, if you have it, you can also try to introduce nitro group. Usually, when you do the nitration, so when you do the nitration with the HNO3 and sulfuric acid, always you will end up with a mixture of compound. So, this is major, this minor, that means both reasonable amount you can. So, you will get always mixture of compound. After the reaction, what we do, we try to remove the this one by hydrolysis, you can get in this way. So, a mixture of compound, but here you can see in this substrate particularly, you can selectively introduce the nitro group, the meta position with respect to that, and with respect to this at the ortho position. So, you can carry out the reaction. This is a recent development in the nitration reactions using transition metal catalysis. You can use FeNO3 as a nitro source. You can do the nitration selectively. So, you have the two aromatic ring. Among this, one of them selectively undergoes reaction, therefore, we call it as chemoselective, and regioselective means you have the different position ortho and meta different positions, but you can selectively try to do the nitration one of the position, therefore, we call this reaction as chemo and regioselective CH nitration. So, the mechanism of the reaction shown here, what happens first to the substrate, the lone pair of the nitrogen makes chelation with the copper 2 chloride, and which then undergoes reaction with the FeNO3 through ligand exchange, and you can get this intermediate transfer the nitro group. Once if you have this one, and now you have the lone pair. So, this nitration takes place as shown here, then so you will have this intermediate and this one. Once if you form this one, then you lose the proton. So, you can get this nitro compound. Once you form this one, they say what you can do, you can try to, this itself very useful compound. This find wide application in medicinal chemistry, because this moiety this known as tetrazole, in place of carboxylic acid they use this one. This has broad applications in medicinal chemistry. If you want, you can try to remove this derivative portion, then therefore, you will be able to get orthonitroaniline as a product. The reaction condition shown here, you can get very good yield. So, if you want to make orthonitroaniline, we are going to see another approach in the next slide, but one of the now the mild method is you can take metal salt with copper 2 chloride, you can keep this substituent here. So, once we have this one, this can chelate with our copper salt, can activate and can bring it the nitro group. So, in this way the reaction can selectively take place this position, you will be able to get the corresponding nitro compound. So, now let us look at the other reaction. In place of nitro group, you can also use nitroso. See here, this reaction has some limitations. When you want to introduce nitroso group, and it works well with the phenol and tertiary aromatic amines, you cannot carry out the reaction with simple aromatic like benzene, and it works well with when you have the OH group in the aromatic ring, phenol and substituted phenol tertiary amines, they work very well. When you use primary and secondary amine, they undergo reaction with the nitroso group. So, the reaction does not take place. Now, let us look at the mechanism of this reaction. So, sodium nitrite, as we have seen earlier we have seen the reaction of nitric acid and the sulfuric acid. Here in place of nitric acid, we use sodium nitrite. Sodium nitrite with the sulfuric acid can form this sodium hydrogen sulfate and HNO2. Once we form this one, this now as we have seen there, it can act as a base, it can deprotonate the proton from the sulfuric acid, and you can form this. Once you form this one, now it can lose water molecule, and you will be able to form the nitrosonium ion as intermediate. This is the actual electrophile in this case. In the previous case, when you take sulfuric acid and nitronium ion is intermediate, here nitrosonium ion is intermediate. Once you form this one, now this can undergo reaction with but in the case of beta naphthol, and how you have to take the beta naphthol with this base like sodium hydroxide. Once if you on basic condition, you will be able to form salt. So, then you add sodium nitrite and sulfuric acid. So, once if you have this one, then you have this can lose proton. Since you carry out the reaction in acidic medium, So, you can get the nitroso compound. Some examples are shown here. The reaction of sodium nitrite with this methoxyphenol is shown. This reaction can be carried out in the presence of anhydrous carboxylic acid. You can introduce nitroso group, and similarly here and para position you have the amide. This also can be carried out. The reaction when you carry out the reaction of this with HNO2 in the presence of copper to sulfate, you can introduce nitroso group. And here an application shown, when you have this derivative heterocyclic compound, you can react with HNO2, the presence of acid, you can introduce nitroso group. Once if you have the nitroso group in the system, you can try to reduce to NH2, and this can be coupled with this one, and you will be able to form adenine. So, synthesis of adenine is usually carried out like this, and you can introduce nitroso group. Nitroso group can be reduced to the corresponding NH2. Once you have this one, now you can try to react and you can get this compound. So, now let us look at sulfonation. So far we have seen the nitration, and the next we have seen the reaction of nitrosonium ion to introduce nitroso group. We have seen one application for each reaction. Now, let us look at the sulfonation. In place of nitric acid, here we are using sulfuric acid. One of these acts as a base, it can deprotonate and you can form this. Once you form this, can lose water molecule and you can make the sulfonium ion. Once you form this one, now this acts as electrophile in this reaction. This selectivity will be similar to the nitration. When you react with benzene, as we have seen, it can undergo addition reaction. You will have this intermediate. Once you form this intermediate, deep cleavage of this carbon hydrogen bond can give this benzene sulfonic acid as a product. So, you can also introduce sulfonic acid substituent as shown here. You can use SO3 in the presence of sulfuric acid. You can make this benzene sulfonic acid. When you react with sodium chloride, you can make the salt. Here the lone pair from the oxygen picks a proton from here. Once you form this sulfonium ion and this salt. Once form this one, as just we have seen, and we have the benzene ring. Just we have seen, it can undergo reaction, you can get the benzene sulfonic acid. Now, let us look at one application. When you take the acetamide, when you have the aniline react with acetic anhydride, if you have the aniline, you can react with acetic anhydride in the presence of base like triethylamine. So, you will be able to form this amide. Once you form the amide, now just we have seen the nitration. If you use a mixture of nitric and sulfuric acid, the nitration take place, and ortho as well as para position will get mixture of dinitroamides, but in the case of sulfonation, selectively the sulfonation takes place at the para position comparing to the ortho position. You can introduce the sulfonic acid group at the para position. Once if you have this one, now you can do the nitration. When you do the nitration, so now since this is electron withdrawing group, this electron donating group, so the nitration will take place with respect to this ortho position, with respect to this one meta position. The reaction is quite efficient. In this way, you can try to introduce nitro group. Once if you introduce a nitro group, when you react with dilute acid, you can do desulfonation. So, you can end up with this ortho nitro derivative. This when you do the hydrolysis, and you can convert into ortho nitroaniline. So, if you want to make ortho nitroaniline, one of the effective and straightforward synthetic route is that you just start with aniline, protect the aniline with acetyl group. Once you form the acetamide, now you can try to do sulfonation. the sulfonation takes place selectively. So, at the para position, so selectively you can introduce the sulfonic acid group at the para position. Once if you have this one, now you can do the nitration, and which can take place selectively at the ortho position with respect to this amide and meta position with respect to sulfonic acid substituent. Once you form this one, now you can try to do desulfonation, and you can end up with this orthonitro derivative. Once you have this one, you can do hydrolysis, you can remove the acetyl group, you can get this orthonitro-aniline as the product. So far we have seen the nitration and sulfonation reactions. Now let us look at the halogenation reaction. The first example involves the reaction of molecular chlorine with benzene to give the chlorobenzene as the product. This can be carried out in the presence of aluminum chloride, and when you have this is a weak electrophile. When you have the Lewis acid, so now the benzene can react this activated electrophile. This weak electrophile, when you have the Lewis acid, you form this kind of activated electrophile. Now, the benzene can react this electrophile, and you can end up with this intermediate. Once you have this one, now this you have this can deprotonate, then you can get chlorobenzene as the product. You generate HCl as a byproduct in this reaction. So, if you have molecular chlorine in the presence of Lewis acid, you can try to activate to a good electrophile. Now, the benzene ring can undergo reaction, you will be able to get this chlorobenzene as the product. And similarly, you can also try to react with Br2 molecular bromine in the presence of Lewis acid, as just we have seen here. Also it can react, you will be able to form so this activated electrophile. Once we have this one, now it can react, and you will be able to form. So, this intermediate, once you form this one, as just we have seen, and you will be able to form the bromobenzene and HBr, and you will be able to generate the Lewis acid. So, to carry out the reaction, you will be able to, you need a catalytic amount of the Lewis acid, and where you will generate stoichiometric amount of the acid as the byproduct in this reaction. You can carry out the reaction of molecular chlorine and bromine. However, when you go for the reaction with iodine, is a very weak electrophile comparing to chlorine and molecular chlorine and bromine. So, one of the, so as soon as you react and you form the iodobenzene, once you form the iodobenzene hydrogen iodide, the reaction is very less effective, it goes back to the reversible reaction. Therefore, if you carry out the reaction in the presence of oxidizing agent like HNO3, and this can react with iodine, and you will be able to form this intermediate. Once this acts as electrophile in this, once you form this one, then this can react, and then you will be able to have the iodobenzene as the product. This is the byproduct in this reaction. Therefore, in the case of reaction of iodine with the aromatic system, if you carry out the reaction in the presence of oxidizing agent like HNO3, the reaction can be carried out to get iodobenzene as the product. So, here an example shown which has been developed in our group, and one of the recent advances in this halogenation reaction, as we have seen, for example, the same substrate, this aniline derivative, when you have this compound, when you take N-halosuccinamide in the presence of trifluoromethane sulfonic acid at moderate temperature, the presence of palladium acetate, and you can try to do halogenation at the ortho position via CH activation. In this way, you will be able to introduce here Cl, Br, iodine, all you can react with the N-chloro, N-bromo, N-iodosuccinamide. You can introduce the halogen at ortho position selectively. Here also, if you look at here, you have two aromatic ring. One of the aromatic rings selectively undergoes reaction. This is because, and when you have the metal, it may make chelation, activate the CH bond, and the halogenation takes place selectively in this carbon. And when you see the substrate, you can carry out the reaction with a variety of substrates. For example, you can carry out the reaction chlorination, you can in good yield. Similarly, you can also carry out the bromination here also, and you can also have substituent like fluoromethyl group, and you can try to selectively do the halogenation in good yield. For example, shown here, you can also do iodination in very good yield. You can have a variety of substituent in the aromatic ring. However, the halogenation can be selectively carried out at the ortho position by activation of the CH bond through cyclometallation, and this can be understood when you go for the reaction mechanism. You have the substrate, the palladium acetate in this case, and you have the lone pair. It may chelation with the palladium acetate, and you will be able to form this intermediate. And once you form the intermediate, it can activate the CH bond through cyclometallation. You will lose one molecule of acetic acid. LH means acetic acid. So, you can make this intermediate. Once you form this intermediate, and this can undergo oxidative addition with this N-halosuccinamide. So, oxidative addition, this is 2, it will go to this intermediate. Once you form this intermediate, now this can give the product by reductive elimination. You can give the product by reductive elimination here, and you will be able to form the halogenated compound. And so, you have one molecule of acetic acid, and then you can regenerate the palladium acetate to complete the catalytic cycle, where you generate this a byproduct. And this is a recent advance you can see here. You can carry out the bromination, chlorination, iodination using transmetal catalysis at moderate temperature and mild reaction conditions to selectively you can get the halogenated compound. There are also methods now available. You can also try to selectively similar way try to activate the meta as well as para CH bond. You can try to introduce halogen atom, so that you can carry out the reaction at milder reaction conditions. Some other reactions are shown here. So, this example involves, in addition to that, whatever we have seen the nitration, sulfonation, halogenation reactions, you can also do the metallation here. And when you have the phenol, phenol can be readily reacted with the mercury acetate. You can get this organomercury acetate. Once if you have this organomercury compound, which can readily now it can react with the Cl minus, and you can have this intermediate. Once if you have this one, when you react with I2 molecular iodine, you can introduce iodo functional group here. Therefore, if you want to make 2-iodophenol, what you can do? You can try to react with mercury acetate. You can make this organomercury acetate as product, which can, when you react with Cl minus, you will be able to make this compound, the mercury chloride. Once you form this one, when you react with molecular iodine, and you can produce the 2-iodophenol, where you generate this as a byproduct. Similarly, if you have this compound furan, you can also try to react with mercury chloride. You can make this organomercury compound. Once you have this halo substrate, then you can try to react with molecular bromine or iodine, and you can introduce bromine iodine second position of this furan derivative. So, these are some of the examples. So, you can also try to introduce halogen, as we have seen. You can do the metallation. Once if you have the metallation, then you can introduce the halogen, as we have seen the previous case, where what you do, you have introduced the palladium metallation, you make carbon metal bond, Then you react with the N-halosuccinamide, N-chloro as well as bromo and iodosuccinamide. You introduce chlorine, bromine, iodine at the ortho position. As we have seen, this is another example for metallation. You can try to react with mercury acetate. You can make a carbon metal bond. Once you metal bond, then you can try to react with molecular iodine and you can do the iodination. And similarly, here also you make a carbon metal bond. Once you form this carbon metal bond, you can try to react with molecular bromine and iodine. In this way, you can make halogen atom in this aromatic system. Here an example shown for the desulfonation. As just we have seen, if you have this phenol derivative, you can try to react with the sulfonium ion, you can introduce para position. Once if you form this one now, for example here, this desulfonation is shown using Br2. This acts electrophile. When you have this one, it can undergo addition reaction, aromatic addition followed by elimination. You can addition, you will have this compound. Once you form this one, this can lose SO3. You can have this tribromophenol as the product. So, addition elimination, basically you have the aromatic electrophilic substituent product. You substitute in place of sulfonic acid, you are here having Br. This is another example. Through desulfonation, you can also introduce halogen, the aromatic ring. Okay, in this example, you can see here the reaction of nitric acid is shown here, and when you have this functional group, you can try to react with the excess nitric acid. You can generate the NO2 plus. So, this acts as electrophile, which can now readily undergo addition followed by elimination, substitution reaction. Once you form this one, in this way you can also remove the sulfur dioxide as you can see here, and you can try to introduce the nitro group. This is also another example for electrophilic substitution. This when you have the phenol group, and this can readily undergo reaction with this nitonium ion, and then you can lose SO3. In this way you can introduce the nitro group. In summary, today we have seen three important transformations. The first one, we have seen the nitration. There are several approaches are available to for nitration. So, we have seen one of the common method that we use in the laboratory. If you have the nitric acid and sulfuric acid, you will be able to generate nitonium ion. Once you form the nitonium ion, which can act as an electrophile, which can readily undergo reaction with the aromatic system like benzene, can undergo addition followed by elimination. You can get the substituted compound nitrobenzene. And if you have the electron withdrawing group, reaction is very slow. We have seen one example. If you have the nitrobenzene, when you do introduce another nitro group, the nitration takes place meta position. However, you have to carry out the reaction at higher temperature. On the other hand, if you have electron donating group, for example, if you have the methyl group, the reaction is facilitated. For example, if you compare the reactivity of benzene with the toluene for the nitration, the toluene shows 25 times greater reactivity comparing to benzene, because the benzene ring, when you have the electron donating group, the electron density is rich and very good nucleophile. It can readily undergo reaction with the electrophile and can undergo the substitution reaction. And then we have seen one example for the synthesis of methyl orange. You can make a diazonium salt. You can try to reduce the nitro group using tin HCl. You can then react with the sodium nitrate HCl. You can form the diazonium salt. Once you have the diazonium salt, you can try to react dimethyl aniline. You can make methyl orange, which we use indicator during the titration to find out the pH of the reaction medium. We also have seen introduction of nitroso functional group. If you have sodium nitrite and when you react with the H2SO4, you can produce nitrosonium ion, which acts as electrophile. When this reaction has limitations, whenever you have the substituent like OH group or tertiary amino substituent, those substrate only can undergo reaction. You can introduce the nitroso group. We have seen one example also. You can try to reduce the nitroso group to amino group that can be used for the synthesis of adenine. We have seen one example. Then we have seen the sulfonation reaction. So, in place of nitric acid, if you have the sulfuric acid, you can also make sulfoxonium ion, which can act as a electrophile. One of the sulfuric acid acts as a base, another acts as an acid. You can make sulfoxynium ion, which can act as electrophile, which can undergo reaction. Where we have seen one example, if you have the amide substituent, you can introduce the sulfonation at the para position, and this once if you have this one, this can be further reacted. For example, you can do the nitration, then you can do the desulfonation. In this way you can make orthonitroaniline. We have seen one example. This is a very important precursor to make variety of compounds. Then we have seen how you can also carry out halogenation reaction, and bromination, chlorination can be carried out using molecular chlorine, molecular bromine in the presence of Lewis acid like aluminum chloride, and FeBr3 you can introduce the halogen atom in the aromatic ring. And if you have, in the case of iodine, we have seen that you have to use oxidizing agent like HNO3 to push the reaction forward. So, in HNO3 the reaction can be facilitated, you can make the iodobenzene. Then we have seen also examples where you can use the metallation. For example, if by chelation you can introduce the palladium metal if you have the aromatic ring. For example, we have seen one aniline derivative, we have the tetrasol substituent which can make chelation with your palladium, activate the CH bond, you make a carbon palladium bond. Once if you make the carbon metal bond, you can try to react with N halosuccinamide like N chloro, N bromo, N iodosuccinamide. You can undergo oxidative addition followed by reductive elimination. In this way you will be able to introduce halogen atom, and this reaction can be carried out at moderate temperature. Then also we have seen the other approach, you can also use metallation. For example, if you have the phenol substituent, you can try to react with mercury acetate and you can make the organomercury compound. Once you form this one, then you can try to react with molecular iodine. In this way you can do the iodination. We also have seen the case of furan, you can also try to react similar way with mercury chloride. You can make the organomercury compound. Once you form this one, then you can try to react with molecular bromine and molecular iodine. In this way you can try to introduce bromine and iodine in the case of furan. So, these are very fundamental and important reactions, organic synthesis. We often use these reactions to make this compound which serve as precursor to construct a complex molecules. With this we conclude this lecture. Thank you very much.